Welcome to this explainer. Today, we're diving into the absolute high-stakes race for the most prestigious awards in modern physics. We're going to look at a discovery so incredibly small, yet so profoundly impactful that it has completely set the scientific community on fire. Okay, could twisting a single piece of carbon by just a microscopic amount totally change the future of computers and win the ultimate prize in science? I know, it sounds straight out of science fiction, but it is happening right now in labs all over the world. To really grasp the magnitude of this discovery, though, we first need to understand the intense arena these scientists are competing in. We're talking about the Nobel Prize. It is, without a doubt, the absolute pinnacle of scientific glory. Winning it grants this immense historical prestige, literally placing a scientist's name right up there with Einstein and Curie. And, of course, it comes with a massive monetary reward of 11 million Swedish kronor. That's roughly a cool million US dollars. It's the ultimate validation of a lifetime of work.
But actually getting your hands on that medal, it is a grueling, super secretive gauntlet. Every year, only about 3,000 confidential invitations are sent out globally to prominent academics to nominate candidates. The deadline is an incredibly strict January 31st. And here's the craziest part. The nominees are never publicly named, and all nomination records are locked away in a vault for 50 years. 50! It's a highly secretive process designed to reward only the most paradigm-shifting discoveries. Big science isn't the only way to win. If we look at the prediction markets for the upcoming 2026 Nobel Prize in Physics, we see forecasters are actually betting heavily on a very different scale of physics. Quantum mechanics is leading the pack at 37%, but right behind it, tied with astrophysics, is condensed matter physics at 24%. Condensed matter physics is basically the study of solid and liquid materials, and right now it is experiencing a massive revolution. And that brings us to the ultimate dark horse of condensed matter physics right now. It's a mind-bending new field called Twistronics. Twistronics is exactly what it sounds like. It's the study of how the electronic properties of ultra-thin two-dimensional materials completely change when you stack them and twist them at very specific angles. It is currently the absolute hottest topic in physics. What's amazing is the founding breakthrough of Twistronics happened really fast, and it happened in a single lab at MIT. It was led by physicist Pablo Jarillo-Herrero and a brilliant 21-year-old graduate student named Yuan. Just think about that for a second. The guy was just a few years out of high school, and they weren't using giant particle accelerators. They were just using incredibly thin sheets of carbon. The contrast they discovered is literally game-changing. You've probably heard of graphene from your chemistry or physics classes. It's a single atom-thick layer of carbon, exactly like the graphite inside your pencil. On its own, a normal sheet of graphene is highly conductive. But when Jarillo-Herrero and Cal layered two sheets together and gave them a twist, the material gained entirely new superpowers. Depending on the electric field they applied, it could instantly behave as a complete insulator, blocking all electricity, or as a perfect superconductor. But here's the catch. They couldn't just casually slap these sheets together. They had to offset them by an incredibly precise, mathematically calculated angle, exactly 1.1 degrees. In the physics community, this has officially become known as the magic angle. Achieving this in the lab is exceptionally difficult, mostly because the carbon sheets naturally just want to snap back into perfect alignment. To really grasp why 1.1 degrees is so magical, think about tuning a guitar. Imagine you have two strings that are just slightly out of tune with each other. When you pluck them together, the sound is harsh, right? It's messy. But if you twist the tuning peg to the absolute perfect tension, tuning them to the exact right pitch, the strings suddenly resonate together in perfect musical harmony. Twisting these carbon layers by exactly 1.1 degrees does the same thing. It tunes the behavior of the electrons flowing through them into a perfectly resonating, harmonious state. At that exact 1.1 degree angle, the overlapping honeycomb shapes of the carbon atoms create this larger grid called a moire pattern. In this pattern, the electrons literally hit the brakes. They slow down so much that they actually start to notice each other and strongly interact. They perfectly sync up, pair off, and form what is known as a superfluid. This fluid flows through the carbon sheet with absolutely zero electrical resistance, meaning zero energy is lost. When this was published, the physics world basically lost its collective mind. Physicist Corey Dean at Columbia University literally said, "I can't find words to describe how profound that is. I'd have to make something up." He even jokingly suggested calling it dynamic material engineering, and this reaction completely validates how incredibly significant the discovery is. It's practically unprecedented to see superconductivity at such a low density of electrons, especially in a material as simple as pure carbon. So what does this all mean for us? Well, it means the electronics and computers of the future are in for a total revolution. Think about how hot your laptop gets when you're running a heavy program or playing a game. That heat? That's wasted energy caused by electrical resistance. With Twistronics, we could discard those bulky, multi-layered silicon chips entirely.
We could build complex, diverse circuits directly into simple, atom-thick carbon sheets. With zero electrical resistance, these future computers would process data at lightning-fast speeds without ever overheating or wasting a single drop of energy. It might even be the key to practical quantum computing. We are literally standing at the starting line of an entirely new era in physics and materials science, all born from just a simple twist. Which leaves us with one final, exciting question to ponder as we watch the future unfold. Will this simple, elegant 1.1-degree twist in a sheet of pencil lead be the massive breakthrough that takes home the next $1 million Nobel Prize? I guess we'll just have to wait for the committee to open those secret envelopes to find out. Thank you so much for joining me on this explainer, and definitely keep your eyes on the magic angle.